In this video, I'm going to describe a technique within Mathematica in which you can solve an equation that depends on a parameter and that requires an initial guess in such a way that you step the parameter along bit by bit and use the previous solution as the initial guess for the solution at the next value of the parameter. This will become more clear as the example unfolds. So the example in this case has to do with the trajectory of a projectile, which is launched at an initial velocity v at an angle theta above the horizontal. And so I've written here two functions, x and y, which describe the horizontal and vertical position of the projectile as a function of time. I've also defined a function here, trajplot, which plots the trajectory for a given initial velocity and launch angle out to a certain maximum time. So I'm going to make sure these are defined, and I'm going to test this function by giving it an initial velocity of 10, a launch angle of pi over 3, this is in radians, and a maximum time of 2. So here's the trajectory, a parabolic arc. Now, Mathematica has a useful function for seeing how the result of a calculation, typically some plot, but it could be something else, varies as you change a parameter controlled by a slider, and this function is called manipulate. So here I'm using manipulate to control the trajectory plot, traj plot, by changing the angle, the launch angle. And so if I execute this, then I can vary that launch angle, and you can see that as I increase the launch angle, the distance that the projectile travels before it lands on the ground again steadily increases until the angle gets up to about, as it turns out, 45 degrees or so. In fact, exactly 45 degrees. And then, as you go launching it more and more vertically, of course, the projectile travels less distance downrange until when you're launching it basically straight up, it comes straight down again. You can actually see what value you've set if you click on this little plus sign, and it will show you the value of the parameter that you've set, the slider. So now, in principle, you could use this slider to vary the angle and find out where the projectile landed by reading it off the graph, or if you wanted the projectile to land at a particular spot, you could vary the slider until it landed more or less where you want. If you want to do that more precisely, then you can use FindRoot to find the launch angle theta that lands the projectile at a desired location. So for example, suppose you want the projectile to land at x0 equals 2, which is pretty close, and you're going to do that by shooting it high. So FindRoot takes an initial guess for the angle theta, which in this example here, I've taken that initial guess as theta of 1.5 radians, which is actually quite close to vertical, over here someplace. And then the equations I want to solve are that x0 at some time and that launch angle is 2, and y is 0 because the projectile is back on the ground again. And so I'm solving for both the time and the angle, the time that it lands and the angle needed to make it land at that spot. And so if I do this FindRoot, then I get the time and the angle. Now, it would be more convenient if I had a function that I could give the desired position and the initial guess theta that would give me the pair of results that I want. And so here I'm defining a function, adjust angle, where I hand it the position I want and my guess for the theta, theta 0, and it gives me back a pair of values, the x0 that I asked for and the theta that really works. And notice the syntax of the function. So the way it works is it does a FindRoot. Okay, here using theta 0 is the initial guess. Okay, rather than the 1.5 that I stuck in here, this argument of the function is used as the initial guess. The FindRoot will produce a substitution rule like that, which I then use to substitute the pair x0 theta, and the effect of that will be that the theta is replaced by whatever solution it found. And what the function will do is return then a pair of values, x0 and the theta that actually works. So I can test this. Again, if I ask for x equals 2 and make the initial guess of theta of 1.5, but I use my function adjust angle, then what it will do is it will return the value 2 that I asked for and the theta that works. And here I've saved that in the pair of values x0, theta 0. Now I want to use this function adjust angle to make a table, a targeting table as it were, of landing positions x0 and the corresponding launch angles theta. And I want this table to have x0 varying from 0.25 to 10 in steps of 0.25. So here is how that's done. I am going to save the results in something called angle table, and I'm going to do this by making a table. Okay, so in general, what table does is to make a table in which some function is evaluated, here something simple like z, where z ranges from 1 to 5, or I could make a table of z squared, or I could make z vary from 1 to 5 in steps of 2, and that's the syntax of table. Here we do something special inside the table. The table, x0, as I said, ranges starting from 0.25 to 10 in steps of 0.25. But the thing that's inside the table is a little bit tricky. So first of all, here's adjust angle with x0, which is the thing that is being stepped in the table, and theta 0. And I catch the answer from the x0 in this pair x val and theta 0. And so you see the effect of that is that each time the table evaluates a new result, it replaces theta 0, whatever it was, by the result that adjust angle gives. In other words, the actual theta. And then the next time the table evaluates the next result, theta 0 will be not whatever it was originally, but it will be the most recent angle returned by adjust angle. And in this way, you walk along the table, continually adjusting the initial guess so that it is the previous solution. So if I execute this line, then I get a table of results, which is more easily looked at with table form. And so you can see that the angle for 0.25 is 1.5583, the angle for 0.5 is 1.54, and so on. Of course, to see the shape of that is not very easily done with the table, so I'd rather make a plot of this. And really I'd like to plot the downrange distance x0 versus the launch angle theta, since that's the thing I'm adjusting. I want the x0 to be the vertical thing on the plot and the theta to be the horizontal. Right now, this table is built in such a way that the x0 is the first thing and the theta is the second thing. So that would lead to theta being the y in the plot. So I'd like to reverse the order of those columns. And here I can do that. This little piece here has the effect of making a new table in which the columns are reversed. So what this is basically doing is selecting all rows of the original table, angle table, but giving me back the columns in reverse order, giving me the second element of the row followed by the first element of the row. And if I didn't want all of the elements of the row, I could just use a 2 or a 1 here, and it would give me only the second element or only the first element. But this syntax allows me effectively to reverse the order. So for instance, if I have a table which is just a table of z and z squared, and I save that in a variable tab, then if I take tab all rows and then the second column followed by the first column, I get, instead of 112439, I get 114293, etc. I've reversed the order of the columns. So I use that to reverse the x0 and the theta to make a plot in which x0 varies with theta, and then you see that the maximum x0 corresponds to a certain angle, which it turns out is 45 degrees, and as I increase the angle further, that is, shoot more and more vertically, the x0 drops until basically I'm shooting it straight up and it comes straight down. So to summarize, I've demonstrated three important techniques. One is defining a function that uses FindRoot and returns a value. And so the way that's done is by having something here which is substituted by the result of FindRoot so that I get numbers coming out, here a list of numbers, rather than substitution rules. The second technique is this business of stepping a parameter, here the initial guess for a just angle, the guessed value of theta, is stepped along as I generate new values, changing the target position so that the initial guess is the previous solution. And this is a very general technique that can be used anytime you're trying to solve an equation that requires an initial guess, and the initial guess needs to be a good initial guess, and so you can step a parameter and take the initial guess as the previous solution. The third little trick is how you go about changing the order of columns or selecting columns in a table of data which is some number of rows and some number of columns. And so this general syntax is useful for doing things like reversing the order of columns or selecting only one column or selecting a subset of columns or what have you.